is a electronic design automation tool, or you can say spice tools, which you might have been having idea of. You might have worked with PSpice earlier. Last year we also conducted a multi-sim workshop, which is also a similar tool. But what's new and what is Cadence actually? Virtuoso. Cadence is a tool which is used in lead, leading companies in the industry use Cadence for designing their circuits, packaging and layout routing for the circuits. So they use Cadence. Why they use Cadence is because Cadence is flexible enough that a person can design his own circuit according to his design specifications from the scratch. So it is called full custom design in VLSI. That's why Cadence is widely used tool and is most important for any one of us to learn. What I feel is, even if you don't have a basic idea of circuits and all, if you are interested to learn, then you can actually learn it. The interest is the main thing to learn this tool, and it would be similar to multisim or PSpice, but bit more. You can do more kind of analysis for your circuits, and it will be helpful for you, I guess. So what in this workshop I have planned is I will give you a basic idea of how to characterize the BJT and MOSFET transistors. Then if time is there, then we can see how to analyze the uh, parameters of CMOS inverter, which is not gate. What parameters we will analyze for BJT and MOSFET is any transistor, what shall it perform actually when we input a, when we give an input voltage. What is the basic function of transistor? When we give some input voltage and provide a DC power to it, then it should transform the input signal and transform the input signal in such a way that we get the desired response from it by taking the power from the DC signal. So that's what the main function of transistor is, and we have to design its what design its parameters, such as maybe current gain or maybe the area, width and length of the transistors. We have designed in such a way that it performs our required function. By when as bipolar junction transistor BJT is considered, um, BJT is actually function is similar to that of diode, but it has, you're following, right? I cannot see messages in the chat box because
Yes, continue.
okay. Yeah. So what we do, sorry for the noise. Yeah. So we are discussing the BJT transistor. What BJT is actually? BJT is similar to diode, but it has two junctions, whereas diode has one junction. What is the function of BJT means? Whenever we bias, suppose we take an NPN transistor, um, we bias the for one junction in forward bias mode and one junction in reverse bias mode. Then the electric field applied across this transistor is transferred to collector, and that uh, is done in such a way the device structure performs the function in such a way that the reverse bias, with the help of this reverse biased voltage and with the help of this forward bias voltage, the entire input power is, most of the input power is transferred to the output. And if you want to characterize Without discussing much about BJT, that might have been discussed in your classes or given in books. So I will tell you how what we are going to perform in this particular workshop. What we will do is for a BJT transistor, uh, suppose we need to characterize it. How we need to characterize? We will apply a particular input, and we'll see what is the response of the circuit of the transistor for that particular input. We measure the output, so that's how we find the output characteristic. So I have taken CE mode of operation, which is mostly used in most of the circuits. There are reasons, but we won't look into that. We will characterize this transistor and find its IO characteristics in this workshop. So how do we characterize transistor? We apply a particular voltage, and then some amount of current flows through it if this is greater than the threshold of this transistor, and for that we'll get some output current according to the transistor's properties, which are given when manufacturing, or we can actually mm, given by the model which is given in the model library of the simulator tool, right? So for that we will characterize this transistor. Why we are placing resistors means BJT may burn off, the diode may break off due to abrupt changes in voltages. So that is the reason we keep a resistor. Then after doing that, this is how the CE mode characteristics looks like. For those who don't have idea of how the characteristics would be, I have attached these figures from a reference book. So whenever the input is greater than the particular threshold, then we can expect some amount of current flow transfer from input to output, right? So in NPN transistor, uh, as this block diagram indicates, in an NPN transistor, the first one, current flows from collector to emitter. This indicates the flow of current, and whereas in the PNP transistor, current flows from emitter to collector. So that is the difference, and there are advantages and disadvantages of both type of configurations that we won't look into. So the main idea of this workshop is to get you acquainted with Cadence, so that you can perform, you can do uh, your, you can implement your circuits and get to know what are the difficulties in implementation, and you can know how to design those circuits when required specifications are given. So more I want to explore on the Cadence tool. This can be done anyway without any explanation. You can read as well. So there are three modes of operation for a BJT transistor. Uh, when input less than threshold is applied, then transistor is off, and that is called cutoff. And when a adequate amount of input is applied, the transistor, certain amount of current flows through transistor and it operates in linear region. But when you apply high input voltage, then what happens to the transistor is the maximum amount of current that can flow through the transistor is limited by the electrons and the speed of electrons. So when that happens, the transistor actually saturates. So the maximum current is limited. So that's what the saturation is. So after this, we will see MOSFET. But before seeing to going to MOSFET, we will first simulate BJT first. So I think most of you have installed Cadence, right? So I hope most of you install Cadence, and if installed, then open the VMware workstation.
Yes.
So I guess everyone of you or most of you have installed this. Actually, this software, if you want to get the development kit, which can be used for fabrication in the industry, it is licensed. So we won't get that. I mean, we cannot get that. So we have given you a GPDK version, which is actually given to the people who license who take license of it, but we can also uh, we have collected it from the faculty, so who have taken from the lab who have taken the license, so they can distribute GPDK file to students. So that's why we are given it. And now you can try opening a virtual machine. So we have already installed Cadence, so we can using that application we can open this. So click on open virtual machine, and in the Cadence Virtuoso folder, in this particular folder you can see actually in the Cadence IC design virtuoso folder. From that you can open this virtual machine. Can everyone open this? Hello.
Yeah, yeah. Others, please put in the chat box if you are able to
Yeah,
open,
because we won't be able to know whether you're
or you can just
following.
unmute your mic and ask if any have any problem.
Okay. So my screen is visible.
Yes, it is.
The yes. Are okay. Now power on this virtual machine. So it will take a while to open. Actually, the Cadence which we have installed as the Linux OS, which is given by Red Hat Enterprise, is already there in that files, and it gets booted up. So can everyone able to see the lock screen of the virtual machine?
Yes.
Yeah. Then we can log into this virtual machine. The username is root. The username is root, and the password I'll put it in the chat box. It's 6 ones. Password is 6 ones. So we can log in to the virtual machine. Once you log into the virtual machine, you can see these folders already uh, made before you install this tool. So you can open root's home. Then in this you can open Cadence by opening the terminal. Right click and click on open in terminal. Then enter V. Press V and press enter. Then the Cadence tool. That's a shortcut created to open this software. Other way is to source the CSHRC file, which can also be done, but this is way short way. So is everyone following it and able to do parallelly with me?
Yes.
This may seem as if it may not be required for you, or it may be you may feel bit advanced or bit unnecessary for you, but for those who want to work in VLSI area and do some basic projects and learn how to actually design circuits and implement them practically, so they will find it an very useful and important tool. And we are lucky to get this software onto your computers. And yeah, and in final year projects as well, we won't use simple piece or multisim because that is not that much flexible enough to modify our designs in such a way that our specifications are met. So the industry level tools are preferred. So once you, I think Virtuoso tool has been opened for everyone, has opened for everyone. At least some of you, one of you can respond. Anyone from?
Excuse me.
Yeah.
In the roots home, what is the name of the file you should open?
No. In the empty space, you can just click on right click and click on open in terminal.
Okay.
Then in open in terminal, then press V and click enter. Then the Virtuoso will open. Cadence Virtuoso.
Yeah, thank you.
Once this is open, um, yeah. Once this is open, click on file. Click on file. So to start with the simulation, you need to create your own library where you can save the schematic or any kind of layout or whatever circuits you want to simulate. So as soon as you open the Virtuoso, click on file and go to create new library. So let me create a library which is not there already. So click, let's see, workshop October 18. Then by giving a name, you can give any name which can include numbers and alphabetical letters, but not special characters other than underscore. So give a library name and check the attached to an existing library, because we are not going to define our own libraries. There is already a library given to us which has the models of these transistors and resistors, capacitors, and everything, so which we can use it. Uh, that is the GPDK library. So click on attach to existing library and then click OK. Then it will ask which library you want to attach to it. Analog library is the one which has the ideal components but which cannot be used for practical design. So we will attach the GPDK library for this. Now whatever the library you attach to play, it is important when we go to the physical design, which is when we draw the layout for the circuits. Then it matters because we need to extract all the rules for that particular model. So click on GPDK 180 and then press OK. Then that will, then a new library is created. So it will give the message design library workshop October 18 successfully attached to GPDK 180 library. So I hope everyone is able to create a new library by attaching it to GPDK 180 tool, GPDK 180 technology library, right? Have you done that, or do you have any problem in creating a library? Uh, can I just know how many are doing parallelly with me? At least 10 to 15 people, around 30, or if it's good if then if most of you are doing. Just type whether you are doing or not, yes or no. Yeah, technology libraries, GPDK 180. So first I will show again. Just click on file, then you have to create a new library, then give a name here. So you have to give a name to the library, which can be include capital alphabetical letters and numbers, and no special characters other than underscore. Then you give a name, then click on check the attached to existing technology library, then click on OK. Then you will get another window asking which library you want to attach to. Then in that select GPDK 180 and then you click OK. That will be created, and this message will be displayed. This message GPDK 180 successfully workshop library successfully attached to the technology library. So I don't want to take much time here. Now if you want to create a new cell view, let us say, then we will create a new cell view. So go to new, then cell view. So you want to create a simulate any circuit, then or design and simulate any circuit, you need to create a cell view for that circuit with the help of the library in the library which you have created just now. So click on new cell view. Then it will ask in which library you have to actually create this. Then I will select I want to create it in the workshop library. Then let me give the name as will simulate NPN characteristics in CE mode. So let me give it a name NPN characteristics in CE mode. Right? Then giving the name, just check that whether the type is schematic or not. Schematic in the sense you will have the symbols or a symbolic representation of the uh, circuits you are working with, and you just drag and drop and you give the values which you want to simulate with, then you can run your simulation. There are other many types of files you can actually do. After schematic in the design, we generally go to layout one, which will where we lay the circuits. We are not going to see that now. So first, as of now, uh, just check whether schematic is by default. It will be schematic. So just check whether this is fine or not. Then click on OK. Then a new cell view is created and a tab is open, which gives us which is empty tab where we need to place our circuit. Right? I hope everyone have created a new cell view. If everyone has created a new cell view, then we can go. Otherwise, if you are lagging by something, then you'll be missing one point, and you may take everything may go because you may not be following. So I hope everyone has created. I hope everyone of you have created a cell view. Then okay. Then we will start adding our circuit to the. We'll start uh, making our circuit. Right. So to make circuit, we need to insert the NPN transistor now. So just I think everyone has created cell view by now, and I'm starting how to actually draw the circuit here. Just click on create. We need to add an instance. Add an instance of the component which we want to add to our circuit. You can just go to create and uh, do like that, or just simply press I, then that window will open. Then browse for the component which you want to attach. So since the technology library is GPDK180, you click on that, then it gives us the list of components which are available in that library. There are MOS transistors of different models. There are resistors, capacitors, BJTs and all. So we want an NPN transistor, just type NPN, then we will get a simple model NPN transistor. We want, since we are simulating the schematic circuit, then just click on symbol, double click on symbol, then we will get the symbolic view of the transistor in the schematic. So and just click on hide and put your transistor, place your transistor here. So one transistor will be enough for our characterization. So I have placed one transistor, right? Are you able to uh, add a component to your schematic cell view? Any one of you can just reply so that I can go for.
Yes.
Okay. Once a component is added, then we also need a small biasing resistors to avoid the damage of the transistor. So we are also going to add that resistor. Just click on I to add an instant. Then in the same library, you can type a resistor, RES. If you type, then you'll get a resistor. There are another resistor, the GPDK 180 library, then type resistor. Okay, actually these resistors are poly resistors which are available in this, because only we can manufacture poly resistors with what the advantage of poly resistor is that the capacitance effect will be less when compared to metals, and polyesters can be easily fabricated on the chip. So in the model library, most of them are polyesters. So for our simulation, we can take resistor from the analog library, which gives us an ideal resistor. You can type RES, then you will get a just click on the analog lib and just type RES, you will get a resistor. Then just click on the symbol, right? Then it will give us a resistor. So we need one resistor at the base and one resistor at the collector. So to rotate the resistor, press R. Then the resistor is rotated and place two resistors, right? So I hope every one of you have added these components to your circuit. Then we need to connect this. Okay. Also, we need to add the voltage, input voltage, DC power source, and a reference ground to this circuit. We can add that from by taking the sources from the analog library. In the analog library, we have the sources. If you want a VDC, then you can just click VDC, then a voltage source is shown here. And if you want a constant current source, it's also given here. Want want a ground, a ideal ground reference is given, but while going with practical layouts and all, we cannot actually, when we want to design physically these circuits by routing the wires through the circuits, we cannot use this ideal analog library components. So we can use for simulation, but I am not using as of now. So I'll tell how to power the component and give power to the circuit from the simulation, from the stimulus, from the simulation window uh, by just cancel it by giving we can give an input pins at this point, and we can model the voltages for that pins as and when required in the simulator. So to add pins to this, then just click here or just press P. Just the shortcut is P. Just uh, press P, and suppose let us say we want to add a VCC pin to the circuit, which is the direction is input and the usage is for the schematic, and it gives a voltage, right? So this can be defined even at the stimulus time. So let's hide, and this is the voltage source which we are adding, and to rotate you can just press R, so that direction where we attach the wire will be the input, right? So you can have I have attached a source pin, source which gives us the source for the source of power for this circuit. I want to add a ground pin as well, so I can just mm, give on one more pin and place it here. I want to add one more input pin, let us say VBE as the input that I will place here. We can even add output pins as well. Let's say we will add an output pin. We will add an output pin at the collector of the transistor to measure. We can measure its voltage. We can VC, right? Yeah, you can see for the output pin, the place we need to connect the wire is the end of the other side of the pin. So that's the difference. And now we need, I think everyone has is adding pins now, which will help us in simulating this circuit, which are required for powering the circuit. So is everyone able to create new pins and add? I know you are also working parallelly with me, so you may also not be able to open the meeting tab and reply here. So just put, if you have any problem or whenever I ask, just give a reply so that I will get to know whether you are following or not.
Can you just repeat how we kept the ground pin?
Yeah, just attaching every pin is simple. See the same procedure. Just click on P to add the pins, or else you can also go to create a pin here. Create tab. So create a pin, then you can give any name. It's ground. Direction is, it says ground would conflict with other pins. So let me give another name just for your sake. So I'm going to give an input pin, which is type of input I have added here. So the pin comes. You can place it anywhere. Later we will. I have placed in this manner because we are going to connect them with wires at that particular point. So I have placed VCC at the top so that I can power the collector, and you can give input via base, and I can connect. And since we are operating in common emitter mode, we can connect emitter to ground, right? So to add wires, just click on W. For wire, click on W. Then you will get an arrow symbol like this. So just click on the pin where you want to start with and drag it to the point where you want to connect it. So this is connected. So we have connected emitter to ground. I have to connect collector to resistor. So I have connected. And I have other terminal to power source, and base to input resistor, and resistor to input terminal. Not placed at the exact point, so it is not connected. Let me do it again. So we have connected emitter to ground and input at the base and output at the collector. So let me take the collector voltage as output. It's not required. Let me take it off. So this is what the circuit connection. Then just click on escape when you finish connecting it. So all of you connect the circuit which for characterizing the transistor in common emitter mode. And suppose if I want to see the properties of this BJT, you just check and save the circuit. In the top left corner you can save the circuit. It will check if any pin is left unconnected or connected in a wrong manner, and it will give you a warning or error. So you can see to enlarge this, just fit it to the screen by pressing F. By clicking on it. This is not working for me. Yeah. By clicking here, I am not able to see the properties. Everyone has added these components, right? And connected them. Save the circuit. Pins are visible. What happened to this transistor? I don't know what happened to this. I think when you click on the transistor, you are able to see the properties. Let me open it again. I'll open. I think it got hang or something. Is everyone able to create this circuit?
Yes.
Yes.
Why this isn't working? Oh, doesn't exist. Workshop library doesn't exist. Okay, I guess what happened is yesterday or some other time I created this library and I deleted it in the morning so that I can create now. But since it is open, the library is not updated here, so the library has got deleted, so it's not working. I'll just create another circuit with them in another library. I'll just create. So I have already have this file, I guess. This is MOSFET. Yes. Yeah. No, also it's not. Are you able to select the component? Hello.
Yes, yes.
What's the problem with me? It's not showing any error as well. Okay, let me open this again. Then once you have done that, you can change the value of resistor or value of the transistor. Means for BJT, specified models are given, but whereas MOSFET is considered, you can adjust the parameters as per your requirement. Yeah, it's working fine. Maybe loading problem of any library. Yeah, now here you can observe how it is connected and what are the pins, base, collector, emitter here, and the name of the transistor and the library from which it is taken and the area occupied and all. Multiplier means if you want to connect 10 transistors in parallel, then this is actually used for matching in layout, not required as of now. Okay, save the circuit. Since you have added pins, I will remove this voltage sources. Add pins VCC, ground, and VBE. Ground. VBE. All three got error. Yeah, as of now, we don't require that output pin. You can just click on that output pin and delete it, or you can keep it as it is. Once you have created these pins and connected, save the circuit. Once circuit is saved, if it doesn't give any errors, then just click on. You can change the resistor values first. Let's keep a resistance of 500 ohms, or you can type 0.5k in the resistance. And at the output, a small resistance will suffice. A resistance of 100 ohm is enough. So you can change the resistance values. At the collector, put the value as 100. Just click on the resistor, and in the property editor, change the resistance to 100 ohms. And the input you can give around 500 ohms. So check and save this circuit and go to launch. So now we want to simulate this circuit, and by giving the inputs specified. So go just click on launch ADL window, which is analog design environment window. Just open. I think this window will be opened when you click on that. Are you able to open? Go to launch, then ADL. Right. Once ADL window is open, we need to give the inputs and power to this circuit. So we need to give the stimulus. Right. So in stimulus, you will be seeing this pins which we have added. So VCC, we need to enable this pin in the circuit. So just click on this pin, this particular stimuli, and then go to click enable, and the function is for which we are using is as a DC voltage. So let me give a DC voltage of 6 volts, and the type is voltage. Then apply. So we can see that this is turned on, this pin is turned on, the DC voltage of 6, and ground we are taking it as a reference with 0 volts. So just click on read 0, just enter 0, enable it, and keep the function as 0, apply. Then you should also enable the input pin, and its function also is DC. So the transistor which we are using has as usual around 0.6 to 0.7 volts as threshold value. So let me give voltage more than that, including the resistor drop. So let us give around 1.5 volts. Right. So now you can see that all the pins which you have added in the circuit are turned on, and when we simulate this, these voltages are applied in the circuit. Right. So let's click on OK when each and every stimulus is applied. Now you want to choose which type of simulation we want to use. Since we are given each and everything as DC voltage and all, so let's do the simulation for DC operating point of the circuit first. Just choose analysis as DC, then save DC operating point, click on OK. Right? Is everyone able to add stimuli to the circuit and enable all the pins? I think I've gone a bit faster. No. Can I get at least 1 or 2 responses?
Yeah, it's done.
Yeah. Once you have, once you have to choose the analysis as DC and click on save DC operating point, and once we run this circuit, before running you ensure that you have saved the circuit. Click on check and save in the circuit. Then in the ADL window, click on run by choosing the simulation you want and saving the DC operating point. Then just click on run. Then a window will open which gives us the summary of the run, and when you see like this, then it seems it's successful. It will show the summary here, what all it has run and all. Right. So now to view the DC operating point of the circuit, you can just click here where it's the annotate. Right, in the circuit tab, you can see there is a option called annotate, which by annotating the DC operating points, we get the DC operating points of this particular circuit. So the circuit has an input base current of 29.1.2959 milliampere and beta DC of 45, and so IC which is approximately beta times IB, we get as 58.6815 milli. So if you want to see all the parameters of this particular transistor, just click in the option next to annotate. You can also see print, or just you go to the ADL window and in the result go to print and click on DC operating points. Then when you select the transistor, you can actually view the entire DC parameters of this. What is the base current, collector current, emitter current, transconductance value, the region of operation and all. Right? So I guess everyone is able to do the DC operating point simulation of NPN transistor operated in CE mode. Now let us plot the characteristics for let us first we will plot IB versus VBE characteristics, then we will plot IC versus DC characteristics. So first let me plot IB with VBE, right? So for plotting input characteristics, by varying the voltage input voltage VBE, we need to check what is the input base current. For that, you just create a variable which we give it as create a variable so that we can vary that value for VBE. So in the variables option, click on edit, right? In the variables option, click on edit and name the variable. Let's say variable is X, and this the value means the value at which you want to save the DC operating point. The graph will be plotted for all values, but the DC parameters will not be saved at all points. Right, so let's give 1 volt value. Then I will just add that. So the click on OK. So we can see that a design variable is created. Now we have to give this design variable to the VBE, which is input for the circuit. So we'll just give the DC voltage VBS X, right? Click on apply, so we can see the DC voltage is X, and to vary this X, right? Have you created a variable, everyone, or I'm going fast?
Can you repeat the creation of variable again?
Yeah, just go to variables. In the variables, just click on edit, then give any variable name you want, let's say Y, then just give the value within the range which operates, so that we can save the DC operating point at that value of Y. So we can give, let's say 2 volts, then just click on add, then the variable is created, and then click on OK. The variable creation is done. Once we created the variable, we need to apply this variable to our circuit. To apply this to our circuit, since we want to vary VB and observe IB, so I just give X to VB. The DC voltage is X for VB, and now I vary X. Right, in the stimuli tab, just on VB, just give the DC voltage as X. And when the DC voltage X is given, just we need to modify this simulation. So we need to sweep a design variable X, right? So click on OK. So what you need to do is you need to select the sweep variable. We want to sweep with respect to design variable, which we want which have given the variable. Then you can select design variable from the list of available variables. Click on that and just click OK. You can see this. The design variable, we have given a variable x. Let's say we want to vary x 0 to 3 volts. That is, we want to vary VB input of the transistor from 0 to, let us say, yeah, 3 volts is fine. And sweep type, we want to do a linear sweep. Let's say we give a step size of 0.05. So, or you can give even less one. So we are sweeping x from 0 to 3 volts with a step size of 0.02, and that x is given, since we saved VB as x, this will be applied to the base voltage of the transistor. Just click on OK. Right, so the simulation is set up now. Now we can choose output where we want to measure our parameters. In this, for this, go to just outputs. You need to set up outputs, right? Is it done up to here? Hello.
So can you just repeat for that how to set up the variable?
How to set up the simulation?
No, variable.
Variable, okay. Just go to variables tab here, or just click on here where I'm showing, where my cursor is. The edit variables. In that you can just give a name to the variable, and let me delete these variables as of now. Let's say I want to give a new variable x and give any value within the range, that's fine. Then just click on add. Then put OK. Then you can see that variable is created here. You can see all the design variables here. Now to apply this design variable to a circuit, make the voltage which you want to change as x in the stimuli tab. Stimuli setup tab. Then just click on OK. Then in the design simulation, you want to vary this x. So in the DC analysis, just click on, you want to sweep the design variable and select the design variable x and vary it from, let's say, 0 to 3 with some step size in a linear fashion. So then click OK. Right.
Yeah.
So the design variable x is created. It is given to the transistor, right? So it will be better you follow me and ask, because if I go fast now and if you don't understand now, since what I assume is if I explain first circuit clearly, and if you are able to do that, except the circuit part, everything simulation and adding variables will be same for next circuit as well. So I'll go fast to get you an idea of more 2 or 3 circuits more. So now we need to add the outputs. What outputs we want to view in this circuit. Then just go to click on here outputs. We have set up outputs now, or just in the outputs, just go to setup. Right. So let us select the output from the circuit schematic itself. We won't give the expression. So from design, right? So one. When you go to the set outputs tab, I'll repeat it again for the sake of others. I guess everything is done up to here, and we need to add the outputs now. Just click on outputs setup. Then we need to select our output from the schematic, which is our design. Then click on from design. And suppose, let us say, if I want to measure the collector voltage, then just select this wire. If I want to measure the current at this point, just click here. So then you can see that that current Q0C, whose type is current, is added here, right? And let us say if you want to add one more variable from design, I want to measure the base current because we are doing the input characteristics. Just click on this, and you can see that base current and collector current are added here, right? So let me name the base current as IB, right? Then apply. Okay, so we can see in the analog design environment window that our variables are added, right? So we don't want to plot the collector current. Let me just plot the base current. The save option, what it does is it saves all these values obtained for this base current in a by creating a file, right? So if you want to save, you can save. Let's just plot this variation of IB with respect to VB. For that, just run this circuit. Everyone have added the outputs, right? Hello.
How to design the simulation before you said for input?
How to
Design the simulation for input variable, like choosing the step value and choosing the range. What did you press? What option to press?
yeah, right. Just go to stimuli here in the setup. Go to stimuli, and in the stimuli earlier we have chosen a value for our base voltage, right? So in
Okay.
that, just give the DC voltage as X, right? So whatever the changes you apply in the simulation will get applied to the circuit. Once that is done, just go to. So once outputs are added, just click on netlist and run. Then we can see that our output is plotted, right? This is the characteristics of base current with respect to the varying voltage. Actually, if you want to plot with respect to VB of the transistor without including the resistor value, you can save this file. There is some procedure for that. If there is time, I will go with that later. But as of now, the adding variables and varying that and getting output is important. So I guess everyone is able to do this, right? Now what we will do is we will vary VC at constant VBE and then plot output characteristics. Once that is done, then we will see how we can change both VGS and VC at a time and plot IC versus VC or IB versus VBE at different values of VBE, like that, right? How to change multiple parameters at one time, we will see. So we have plotted the input characteristics. I guess everyone is able to get the plot of input characteristics.
Can you just tell about that setting outputs?
Setting output. So just go to outputs in the ADL window, setup. In the setup, you can select from design. Then if you want current, just click on the base pin, right? If you want, let us say emitter current, just click on the emitter pin which is in red color. Then a circle will appear there, and when you move to setting outputs tab, you can actually see that it is added to the simulation window. Output tab, it is added as output to the simulation window. Is it clear? I have only included the base current for your understanding, and you can actually see what kind of output it is, whether it is a current or you can see the type, you can see the name, you can give it if required. Signal is from the transistor Q0 the base current. That is seen. Once that is done, you just click on netlist and run. Then we'll get the plot of base current, right? So I guess everyone is able to do this. Now let us plot the collector current by varying the VC, right? So you can just click on this output and delete this as of now. Everything is same for collector, but what while plotting output characteristics, what we do is we keep input voltage constant and vary VCE so that we get IC versus VCE, right? So what you do is now in the stimuli tab, let the variable created be same. So let's say we give a DC input voltage of 1.1, even 1 volt is enough. Let's give 1.5 as given earlier. Apply. So the input voltage is kept constant now. And VCC, let's say now we give VCC as X because we need to vary the collector voltage, right? So do this. VCC is given X, VB is given a constant input voltage of 1.5 volts. So now we need to change the simulation. Everything is same. The design variable is X, but now the variable X is applied to VCC. So let us sweep up to 6 volts, 6 or 7, 6 volts. We can reduce step size for faster simulation just for analysis. You can increase or reduce it, it's fine. Sweep type is same, so we just change the range of simulation. Just click on OK. You can see it is sweeping from 0 to 6 with a step size of 50 millivolts, which is 0.05 in a linear fashion, right? So let us say the value at which we want to save the DC operating point as 3 volts, or let us say 6 volts. Click on apply. Okay. So everything is same. So the setup won't take much time. Let me add a collector current output here in the same fashion which I have added earlier. Just go to output, setting outputs from design. Add by clicking on the collector pin of the transistor, add that particular current, then we can see it is added. For convenience, you can rename it to IC, right? Click on OK. Here you click on escape. So you can see that our collector current is added here, and we are varying VCC from 0 to 6. To plot that, just run it. Right, 1 second. So sorry for the delay. Yeah, I guess yeah, my microphone is stuck now. Yeah, the DC simulation for characterizing the output of NPN transistor is set up. Is everyone able to? Did everyone simulate the input characteristics or still lagging? At least 2 or 3 response so that I can go ahead.
Yes, sir.
I guess you are following. So once input characterization is done, let us plot the output characteristics by varying VC. To do that, we just give VB as a constant and VCC as a variable DC voltage X in the stimuli setup, analog stimuli setup. Then just click on you add the output IC in the same way which you have added input base current earlier. Then just run it. Right. So since the entire region of operation is linear, the graph is linear. So let me include cutoff region as well, cutoff as well as saturation region for your understanding. So for that I just change the range of design variables. So let me start from minus 2 volts VCC. We see what happens if VCC goes negative, and let me simulate up to 12 volts. On OK, and done the simulation now. I think this transistor is power transistor kind of thing which has a large range of operation. So, or is there any mistake here? The IC setup in proper manner. Stimuli is clear. Only 0 DC voltage is X. Okay, let me simulate at lower values of VBE. Let's say 1 volt or 0.8 volts for better for low current, right? Or run the same. Yeah. Now we can get you can see the transistor entering into saturation. The transistor entering into the saturation region where the current saturates. I'll explain you once again. What we have given is what we have given you is we are varying the VC of the transistor and at a constant VBE. Here we have given input DC voltage of 0.8 volts and varying this. When we vary this, we are observing the collector current, right? So the collector current varies in this fashion. So we can observe a variation of current with respect to voltage by just press V in the graph. Then you can see by moving this, you can pointer, you can see how current is varying. Negative current at negative voltage at 0, because when you apply negative voltages, the collector base junction is forward biased and you may get negative current. 0 voltages current is very less and it enters, current starts coming and it enters into linear region of operation, right? Fine. So right, I won't spend much time in connecting and all now because it's getting late, so we'll focus on how to characterize it, right? So yeah. So what is MOSFET? MOSFET, we have seen BJT, which operates based on the principle that when an electric field is applied, electrons move from one type of positively or p-type doped semiconductor to n-type, or n-type to p-type, and some current flows, right? But already there is a path for them to flow. Whereas in MOSFET, what we do is we have what we can say, we have a substrate, p type of substrate. On that we have implanted a source and drain, which is doped with n plus ions, which is doped with n type atoms, and they are implanted on the p type substrate, as you can see here. And okay, now we have sorry for the disturbance. We have source and drain implanted on the substrate, and they're separated by a distance L, which we actually call the length of the transistor. And we have a gate which is isolated from source, and drain. On the gate there is a metal which makes contact with the gate, and following the gate there is a silicon oxide SiO2 layer, which acts as a dielectric, or you can say simply a capacitor, which actually prevents any voltage from any current from gate to enter the substrate, right? When we apply a voltage at the gate and it is greater than the value, if it is less than the value which can break the barrier offered by the oxide layer, then the transistor is off. If it is greater, then what happens is, due to the applied voltage, the electrons in the p-type substrate move up, and a channel is created. What we can say that it is not present before, but due to the applied voltage, which is greater than the threshold, a channel is created and current flows, right? So that's the basic idea of MOSFET. And the symbol of MOSFET is this. What is the difference between NMOS and PMOS is, in NMOS we have P substrate and source and drain. Simply, in NMOS the current is due to flow of electrons, whereas in PMOS the current is due to flow of positive type, which is holes, right? That is the difference. The terminals, the gate is the input terminal of, okay, we cannot characterize as input and output, but generally gate is the input terminal, drain is the output terminal, and source is common terminal of this thing. To avoid reverse biasing effects, in NMOS transistor base is collected to ground, and PMOS transistor bulk is connected to the highest power. So the characteristics, the variation of ID, ID with VDS for a MOSFET will be like this, right? So I'll just show you how to simulate a MOSFET using Cadence. So those who have an idea of MOSFET, it's fine, but those who don't have can still try. You can learn complete details about MOSFET later.
Yes.
Yeah. So whatever the work you have done till now, if you want to save when you return to the circuit later on, just go to, in the ADL window, go to session, save state. Then you can save it as state 1. Then just click on OK. Since I have saved earlier state, then it asks me to overwrite state. You can overwrite it. So this is how we save the state. Once we save the state and close this ADL window and we open it again, we can actually load the same state for our simulation, right? So load state in this particular library, in this particular cell view, then we can load this. Everything is there. So that's how we save our work in simulation, right? Next, yeah, we'll create another cell view for analyzing the MOSFET. You can create as given told earlier. Go to File, New. In the library, just give a name NMOS characteristics or anything NMOS. You can give any name related to NMOS and then click on OK. Right. I'll just tell you how to add the transistor. So how to add transistor? Just click on I to add an instance. Then in the GPDK180, take an NMOS transistor. Just click on symbol, add it here. Then we want to give the stimulus to the circuit as which we have given for BJT earlier. So just add input and output pins here as well. Just click on P. Then you can add VDD, ground, and gate. Yeah. Once these are added, just connect them. Once this is done, just okay. Since we have not connected, since we are not connected the bulk of this, as you are not connected the bulk of this transistor, it's giving an error. So just connect the bulk to ground. So the bulk is connected to ground, and just share the circuit, then launch an ADL window for simulation, then set up the stimuli. So you can set up as earlier. I'll just if I have any state, I'll load it. Yes. So you can set up the simulation as shown earlier, and you can add outputs for DC simulation. What we have done is I have given a design variable X, which we are varying the VDS, right? You can see in the stimuli. I have given the drain voltage as X, which we vary. Let's say for this 180 nanometer technology, vary it from 0 to 1.8, or we can vary from 0 to 1 or 0.9 is enough. And gate voltage, we want to plot the drain current by varying VDS at different values of VGS, right? So we will vary gate voltage as well, right? In this simulation, I am varying VDS at particular VGS, but I want to vary VGS as well. So for varying VGS, just listen here. Everything is same as we have done earlier, but now it's a bit different. How to do the parametric analysis with two different variables at a time. So just go to Tools in the ADL window. Go to Parametric Analysis. Then we can vary Y, which is given to the gate voltage. Then we can where we want to sweep this variable, and we can sweep from, let's say, the threshold voltage for this MOSFET is 0.4 volts, which can be seen in the DC characteristics of the MOSFET, as we have seen for BJT. Let's say we vary it from 0.4 to 1.0, right? Even just I'm not saving this simulation, just running it, and you can see that we are varying VDS from 0 to 1, and I will run this parametric analysis. Once this is run, we can see that at different values of VGS from 0.4, 0.55, 0.7, 0.85, at different values of VGS, we have got the plot of drain current ID versus VDS, right? So as you increase VGS, the amount of VDS required for transistor to enter into saturation is more. So you get a line like this which separates the regions of operation. This is how we characterize MOSFETs. So this is how we do the parametric analysis. Shall we simulate a basic CMOS inverter or stop here? Thanks for attending, everyone, and I guess you have learned at least something, and that will be useful to you later. And when you, even if you go for placements or higher studies, having a knowledge of cadence will be really help you later, and you can add it to your resume directly. So, okay, thanks for attending. If there anything is there to say, you can. Otherwise, we'll end this session.